when engineering designers or digital designers, when they come up with some application or some finite state machines, they always start off with the state diagram. Okay, so say you are making a code like in C or Java, you always come up with some pseudo code initially, and then you build upon it, add more stuff to it. Similarly, in the digital electronics, you always start with the state diagram. State diagram means how many finite possibilities we have for some application. So we'll do that for all kind of flip-flops. Here is the schematic symbol right here. So you got S and R as an inputs, and you got clock as an input. This sign right here tells you that this is a positive edge triggered clock. Okay, meanings that the output changes only when the clock goes from 0 to 1. This is 0, this is 1. Here's a small description right here. I'll just read out real quick. It is a very convenient way to visualize the operation of a flip-flop or any large sequential circuit. State diagram is driven by the excitation table. In addition to graphical symbols, tables, or equations, flip-flops can be represented graphically by a state diagram. In this diagram, a state is represented by a circle, and the transition between state is indicated by directed lines or arcs connecting these circles. Now, notice they say a state is represented by a circle. So you see two circles here, correct? So you mean that would mean there are two states. What are those states? 0, 1. Okay, so your Q could be 0 or your Q could be 1. Okay, say you are over here, the present state is 0. Okay, when S and R both are inputs, correct? These are inputs right here. When the inputs are 0 and don't care, what would be the next state? Where it would go from 0 to what state? Looking at the excitation table, what does it tell you? The present state is 0, which is right here. Your S and R, your inputs are 0, don't care. What would be the next state? The answer is in the excitation table. The next state, next state is Qn plus 1 right here, correct? Q next. Next state is 0, right? So that means it will actually stay over here. This is an arrow. Okay, now moving on to this right here. The present state is 0. It will move to state 1 when S and R are 1, 0. Okay, this is S, this is R. Okay, now moving on to this right here. The present state is 1, so we are over here. The next state is going to be 0 when the inputs are 0, 1, and the output is 0 because it's going to 0. Let's move on to the last one right here. When the present state is 1, which is over here, the next state is 1 when S and R are don't care 0. Okay. Okay, now moving on to the state diagram for the D flip-flop. What are those two states right here, folks? 0 and 1. Q equals to 0. Q equals to 1. Again, we look at the excitation table and just follow along. Okay. The next state is going to be 0 when D is 0. Okay. So I'll just say 0 here. Next state is going to be 1 when D is equals to 1. If the present state is 1, which is right here, it goes to 0 when d is 0. Okay. If the present state is 1, it will stay at 1 if d is 1. And let's move on to the state diagram for JK flip-flop. Again, we're gonna look at the excitation table right here. Two states, q equals to 0, q equals to 1. When present state is 0, next state is 0 when j and k are 0 and don't care. Okay. Then moving on to the second one, 0. It goes from 0 to 1 when j is 1, k is don't care. And then moving on to here, when present state is q1, next state is 0 when j and k are don't care 1. Present state is 1, it stays at 1 when don't care 0. Okay. J is don't care. Obviously we know that this is j, this is k, this is j, this is k. So q equals to 0, q equals to 1 here. So when t is 0, it stays here. It goes to 1 when t is 1. It goes to 0 when t is equals to 0. Okay, so that's the state diagram for t flip-flop. It's going to be a 2-bit counter. So in other words, it will start from 0 0 initially, goes to 0 1, then goes to 1 0, and then move to 1 1, and then it will roll over and start from 0 again, and will go on. Okay. So step 1 is the state diagram. Let's define the behavior of our finite state machine. This is also, you see, FSM State Diagram. And in order to create a state diagram, we need to find out how many states we are going to have. So folks, how many states do we need here? Four of them. So which will be 0 0, which is this state, and then the next state is 0 1, then next state is 1 0, and then next state is 1 1. Okay, so it will go from here to here, then 0 1 to it goes to 2, which is 1 0, then to 3, and after 3, where does it go? It goes back to 0, right? Okay, so this is your state diagram right here. Say this is your S0 state, your S1 state, your S2 state, your S3 states. Okay, so 4 states here. Okay, now in a 2-bit counter, usually you the primary input is basically the clock. Okay? So say if this is going to be a positive edge triggered clock, so if initially it's 0, the first positive edge clock comes in, it goes to 0 1. Then the second positive edge clock comes in, it goes to 1 0. Okay, so in order for this to make a transition from one state to another, it has to wait for this clock cycle. Okay. All right, then step 2 is usually transition sequence, which we have already defined, and choosing flip-flop. Okay, because D is the most easiest one, I'm gonna start off with these finite state machine using D flip-flop, but tomorrow we're gonna do JK and SR also. So sequence is already defined. How this will do it. And we will use D flip-flop. Okay. Step 3 is the truth table. Basically the state table. Okay, so we have Q1 and Q0, okay, and then Qn and Qn plus 1. Okay, initially we have 0 0, correct? What would be the next state, folks? Next state will be 0 1. The present state is 0 1, the next state will be 1 0. If the present state is 1 0, next state will be 1 1. If the present state here is 1 1, the next state is going to be 0 0, correct? Remember, Qn and Qn plus 1 here are our outputs, next states, and these are just variable, folks. You can do whatever, D1, D0, and D and Dn plus 1 or whatever. Okay, and Q1 and Q0 are your present states. Okay. Sitting. It will be this then. That's it. Step 4 will be getting the simplified expression using K-map for the next states. So how many expression we would have, folks? Because we have Qn and Qn plus 1, we would need for Qn and Qn plus 1 both. Okay, so 0 1 2 3. Let's do this one for qn, and let's do this one for qn plus 1. Okay, let's look at the min terms over here. So you got 0 here, 1 here, 1 here, and then 0 here. Let's, for qn plus 1, let's look at the min terms over here in this column. So you got 1 here, 0 here, 1 here, and 0 here. So unfortunately we cannot make a pair over here, so this has to be individual right here. And here we can make this pair right here. Okay, so this is going to be, you have what here, q1 and then q0. So q1 q0 bar plus q0 q1 bar. Okay. And q1 plus 1 is simply going to be q0 bar. Okay. This equation for qn, can I also just make exclusive OR gate out of it? Okay, so let me just write it down as qn is equal to q1 exclusive ORing with q0. Okay. Okay. All right. Now the last part, which is the step number 5. Both of them are going to be positive edge triggered. So I'll have my clock here. Okay, I have my D here, I have my Q here, D here, I have my Q here, this is my Q bar, this is my Q bar right here. And just because we have, I'll say this is my Q1 and this is my Q0. So this is my Q0 bar and Q1 bar. Okay. One thing that you should always remember, folks, in case of the D flip-flop, what was the next term? What was the next state was going to be when clock was high? Remember? When clock is high, next state is what? In D flip-flop. It's D, right? Remember? It's D. And where is your D in this design? On the left hand side of the block, right? So this is always going to be your next state right here, left hand side. And on the right hand side, Q1 and Q0, those are what? Present states. I'm also going to rewrite the equations over here. Okay. Now, This next term is equals to Q naught. This is for this flip-flop right here. This flip-flop 0, and this next term is for the flip-flop 1. Okay, so because it's an exclusive OR gate for Q1 and Q naught, okay, the next term for this flip-flop is Q naught bar. And that makes your 2-bit counter. Now, if you want to verify that you got this right, say your Q1 and Q naught are 0, 0, okay, which would mean, what do you have here? 0 and 0, correct? 0, 0 going through exclusive OR gate makes what? Yeah, so this will be 0, okay, and this will be 1, correct? Okay, all right. Now the next clock pulse comes in. What would be Q1? Remember, your next state is equals to D. What is going to be the next state? If you have 0 here, the next state is going to be 0, correct? Q next state is equals to D. Because D is 0, so your next state is equals to 0, correct? Here, what is going to be your next state? Because D is 1, so your next state is going to be 1. So it went from 0, 0 to 0, 1. If you do it again for the next clock cycle, when the next clock cycle arrives, it will go from 0, 1 to 1, 0. Right? So this is how your 2-bit counter is working. So you make flip-flops out of latches, and then you can make registers out of flip-flops. Okay? Register basically storing multiple bits. Okay? So a flip-flop is a 1-bit memory storage device. To increase the storage capacity, we have to use group of flip-flops. This group of flip-flop is known as registers. Okay, so say these are D flip-flops, right? So you got D input right here, and these are 4 of them. I've used the positive edge triggered clock for the most part of the lecture. I'm gonna do negative here now. Okay, this is your output Q, and say you have 0, 0, 1, 0. This is the data that is connected to these. Also, for the sake of, I can say D3, D2, D1, and D0. So similarly, this will be Q3, Q2, Q1, Q0. I got 4 D flip-flop. The data coming to these 4 data lines is 0, 0, 1, 0. What should happen when the next negative edge triggered clock cycle comes in? What should happen? What should be Q3, Q2, Q1, Q0? Because in a D flip-flop, your next term is actually equals to D when clock is high. So it will basically just pass on the data through this flip-flop. It will be 0, 0, 1, 0. Okay. There's another bit, I should not be saying bit. It's a pin, which is clear. Okay, which is usually on a schematic is denoted by this. What would this clear would mean if I again, you know, clear could be active low or active high. We don't want to get into that thing. Clear is what it's going to do is just going to basically reset everything back to 0. Okay. Now another thing which is known as load. Say you have 1 here, 0, 0, 0. Okay. When the first clock cycle came in, it loaded 0, 0, 1, 0, correct? When the next cycle came in, what would be Q3, Q2, Q1, Q0? will be 1000, right? When the next clock cycle comes in, 1000. So basically you will lose this data after the next clock edge comes in, right? How about if you want to store this data for say 100 microseconds or say few seconds? How you want to do that? Any guess? That is where load comes in, right? So if you can, so say for 0010 you want to store this data for 100 microsecond. Okay, so if you set your load, again load could be active low or could be active high. It will be mentioned in the specification sheet. Say it's active low, so if I have the load set to 0 for 100 microseconds, what would happen? It will actually hold this data right here for 100 microseconds. That is what is the purpose of the load here. I'm pretty sure most of you understand the relationship between frequency and time. So if you're looking at a frequency of 1 hertz, basically it's equals to 1 second, right? Hertz. Your basis 3 board has a frequency of 100 megahertz. 100 megahertz. So time would be how much? Reciprocal of that would be how much? 0.01 microseconds, or in other words 10 nanoseconds, right? What does that mean? When you have a clock like this, one complete cycle which contains the 50% duty cycle low, 50% duty cycle high, this is what is equals to 10 nanoseconds. Okay, so it's really fast. Coming to types of registers, so these could be 2 types. One is the synchronous, and the other one is the asynchronous. The difference between the two is flip-flop in case of synchronous is operational, when clock and load are both high. Yes. What? Oh, you mean this? Yeah, Roman too. Yeah. So asynchronous, and then flip-flop is operational only when load is high. Okay. And again, you know, remember load is pretty handy because we don't want to lose our data. Data formats and classification of registers. Data can be entered in serial or in parallel form. Serial would mean, you know, 1 bit at a time. Okay, 1 bit is stored at one time. Parallel would mean all bits at a time. So if I actually go back to my previous, is this a series resistor or a parallel resistor right here? this was a parallel, right? Because it was taking all the bits at the same time. It was not that it was taking this one first, then this one. At one clock cycle, it took all 4 bits, right? So all bits are taken at one time. So again, you know, a block diagram representation could be something like this. You got D in here as an input. Okay. Or this was serial input. This is the serial out, and then this is the parallel out. And then in input serial parallel. So say you have at the input you have 0 0 0 1. Okay, what would be the parallel output to this? Parallel means taking all bits at one time. Okay, so at the input you got 0 0 0 1, so that means it's gonna throw what? And also mention that this is D flip-flop. So you got 0 0 0 and 0. So this is parallel in and parallel out. Okay. Now say if you have serial in and serial out, so say you have a series of data coming in 0 0 0, and initially it was all 1 1 1 and 1. Okay, so when the first clock cycle comes in, what would be the output? What comes out? For after one clock cycle. After one clock cycle, this one will move one here, right? Now what are the new values here? This one will move here, this one will move here, this one will move here, and this 0 will move here, correct? So it will shift to the right one by one on every clock cycle. So the classification, depending upon inputs and output, and another classification is that depends upon application, and those are shift register, and the storage register. So we will do one example of shift register today. Or if you have ever been to a concert, you see those disco lights, they're changing colors and going on and off. Those are basically shift register. They're shifting. You can set the logic to some predefined logic, and then it will do that shifting. Whenever it's 0, it goes off, and it's 1, it goes to. So it makes a certain sequence, and it looks like crazy. that is it. I have one last example, which is gonna be this one right here. Is it a negative edge or a positive edge trigger? Flip-flop. Negative, correct. So you're gonna have your clock here. All the flip-flops are connected to the same clock. And then I have my D input right here, the data that's coming in. So this is flip-flop 2, this is flip-flop 1, this is flip-flop 0. Okay, and all these are connected together, right? The output Q2 becomes the input of this D1 and so on. Okay, and this is going to be an example which will be serial in, serial out. Okay, so let's work on the table first. So initially they all are 0. Okay, so which would mean they all are 0 here. When the next negative edge triggered clock comes in, we have a data here which is 1, 1 and 1 basically coming here. Okay, so when the first negative edge clock comes in, this 1 will move over here, this 0 will move over here, and this 0 will move over here, correct? Right? So what would be the outputs here? You'll have Q2 as 1, Q1 0, and Q0 0, correct? When the second clock comes in, this 1 will move here, this 0 will move here, and what is the new input that's coming in? 1. Okay, then the third clock, negative edge clock comes in, this one moves here, this one moves here, and the new bit coming in, that would be 1, right? So notice after 3 clock cycles you basically have been able to load the data. Also let's look at the timing waveform. So say this is your clock. Okay, and say this is your DN, which was 1, 1 and 1. Initially it was 0, and then it goes to 1, okay. Your Q2, sorry, Q2. What is your Q2 initially, folks? You look at this column right here, okay? Initially it's what? 0, right? So it will be 0 till this point. What happens now? The negative edge of the clock comes in. It goes to 1, right? So you get 1 here, and it stays 1 until the next negative edge of the clock comes in, and it goes to 1 again. So it stays 1 till the next clock edge, and at the next clock it stays 1 also. So it stays 1 all the way from here to here. Let's move on to Q1. So for Q1 you look at this column right here. Initially it's 0, So you got 0 here till this point. The first negative clock edge comes in, it stays 0. Okay, then it goes to 1. And then it goes to 1 again. And then we have Q naught. So we're looking at this column right here. Initially it's 0. And then for 3 clock cycles it's basically 0, 1, 2, and then this is where it goes up and it stays 1. So if you notice here, it's your Q2, Q1 and Q naught making 0, 0, 0, right? Which was this right here. And then next negative edge of the clock arrive, it goes to 0, 0, 1. So you got so this will all 0, 0, 0. This is 0, 0, 1. Okay. And then this is 0, 1, 1. And then this is the last negative touch. 1, 1, and 1. Okay. So you get 1, 1, and 1. So what do you see here? After 3 negative edge triggered clock cycles, you basically have the data that you have over there. So this sums up your serial in, serial out shift register, where you are storing 1 bit and then when the next clock edge comes in, it will move the bit to the right and then take the new bit, and it'll keep on doing that. Okay,